Announcements. They're very quick. Rapid fire torture. Assignment tonight, study session tomorrow, exam Friday, project week for Friday. New assignment and revealed either tonight or tomorrow or next week. So it's a very rapid fire part of the course. We get through this, life will be quite a bit easier for a while. So I've worked a bit with our TA. This is mostly our TA making this, but I looked at it last night / this morning before doing this. This is a how to format a pumping limit proof and just a general overview / he calls it a crash course. But the weaknesses that I've mostly seen are in the setup and statement parts of coming up with a pumping limit proof. So I'll be throwing this on Canvas just for people to review. I thought I'd very briefly go over it just so you get a sense of what it is and how it can be useful to you as you prepare for the regular pumping lemma being on the exam on Friday. And I also didn't want it to detract from tomorrow's study session in case there were more questions or questions about this that I can then answer that don't have to be on the spot. So I'll take a few minutes to go over that and start our class today, and then we will have our typical study session tomorrow. So, general introducing you to the idea, why regular languages, how to think about pumping lemmas, the components, the big components of the pumping lemma proof, the setup, the core logic, and the conclusion. So he goes into an example proof from the first example from class, making it the example that is as simple as possible, the A to the N, B to the N. Then he splits up how to deliver this in two forms, the logical wordy way on the left and the mathematical proof way on the right. So we kind of have two different tracks to follow with regards to how to write the proof depending on which is more comfortable to you. The setup, assumption for later contradiction, the DFA with M states, a suitable string, stating that the length of the string has to be greater than or equal to M, and then decompose W into some X, Y, and Z. Decomposing W broken down into decompose into X, Y to the IZ. Length of X, Y is less than or equal to M, length of Y is greater than or equal to 1, I is greater than or equal to 0, and X, Y to the IZ must be an L for all I. So again, you're going to state all of these as assumptions that you are making. Then in the setup, this is the wordy way on the left and the mathematical on the right to just set up that proof. So come up with and understand one of these ways to make sure that this should be embedded in your proof. This is how you begin that proof. If you're doing it the wordy way, we have to assert that assuming L is regular, we can make the following claims. There exists a DFA with M states. String W, A to the M, B to the M is in L. W can be decomposed such that we meet the following constraints. So we've all done this before, but we see exactly how that gets broken down. Core logic, 3 parts. Where is Y within the structure of W? It must be within the first M characters, but depending on the problem that you're solving, that's going to be constrained to the first M characters, hopefully to some section of just A's, or just something that makes this proof have fewer cases and easier to go through. Then you pick a value for I given that form and show that for any possible breakdown of X, Y, Z within that constraint of where Y must be within the first M characters, that there's a value of I for which we can find the W prime, the string that is presented after having the I repetitions of Y, and then find that and give it evidence that it's not in the original language. If your proof breaks down into multiple cases, you need to do this for every case. So here's what that would look like as part of your proof. The wordy on the left, the mathematical on the right, and then just being able to translate between the left and the right. I think this might help those of you who see it logically, like the wording on the left, to be able to say, well, that's exactly what that means on the right. That's something that I feel like we, as a department, need to do a better job of teaching you how to convert between logical arguments and mathematical arguments. So seeing them right next to each other is really useful for just being able to say, why does the mathy part on the right mean what the wordy part on the left says? And then some additional ideas for this. This is tying it back to the A to the N, B to the N problem. So pumping down, skipping the loop, we have the original string minus the length of y with regards to the size of what we do. Default state is the original string that we came up with. Pumping once, we add the length of y, traversing the loop multiple times. You add the length of y times I minus 1. Since I is 1, you subtract 1 from I to get the number of pumps up that you're doing, which is the number of lengths of y that you are adding. And then conclusion establishes the contradiction and draws a conclusion from that. So just the fact that we were able to find the string is a contradiction, since it's not in the language and it needs to be in the language if this DFA exists. Since that's the case, L cannot be regular via the pumping lemma proof, via this proof by contradiction. So then there's the summary of the entire proof. So this is what the wordy proof looks like from beginning to end, the mathy proof from beginning to end. And some further ideas based on that, based on standard form, a list of some pitfalls, this concept of proof soup. This is something that the TA has seen in a few of the homework assignments where you're trying to pull the proof from an LLM or having an LLM guide you, and it pulls from multiple sources, and because of that, it will mix its variables very frequently. So you'll call a pumping length P followed by something the length of Y, followed by something M, and in the different proofs that it's pulling from, all three of those variables end up meaning the same thing based on where it was pulled from. Even though they're all similar variables to what we've seen in class, it's obvious when your answers are alternating between variable names, but keeping the idea the same, that you're trying to understand something that was pulled from and from multiple sources and kind of put together, stitched together to try to make a valid proof. And even if it seems like it's flowing, you will use a variable you haven't defined, or you will use two variables that mean the same thing, or yeah, it becomes apparent. So variable-based errors, logic-based errors, acceptable shorthands, things that you can shorthand whenever you want to. So this is just a very good, just general overview of pumping lemma proofs and what we can do. And this was awesome that our TA was able to throw this together. So again, I'll be throwing this on Canvas. Feel free to peruse it in a lot more detail as you're studying for the exam on Friday. And if you come up with any questions based on this, it would be great questions to answer or to ask tomorrow and have me answer tomorrow in our review session. Questions on this? Because I have the memory of a goldfish, if you go looking for this in a couple hours and don't see it up, please send me an extremely angry email saying you said you would get this up. What is wrong with you? It's time to go through these and get rid of the ones we're not talking about anymore. All right, last time we were starting to talk about Turing machines. We got a couple of examples of Turing machines in, and we were in the process of doing another one. I think we were going to start the next one. So this was the Turing machine program that accepted the language 0+ or 00 star, same thing. We see the first 0, then we continue to search for additional allowable zeros, and then we move to a final state or a halting state where we can say we've finished parsing the string And now we can accept that the string that was on the tape when we began adhered to 0 ones. Ready for a second example? All right. Let's come up with a Turing machine that accepts a known context-free language, a to the n, b to the n. However, n cannot be 0. We're going to say n is greater than or equal to 1. So assumption you can make, the string that we are going to determine whether it's in this language is on the tape when you begin. The read-write head is on the leftmost character. So what is left of the character that we're pointed to at the beginning is a blank. You can know that beginning. My recommendation for starting this process is to think about in English and logic before you start trying to construct a Turing machine. You have this read-write head that can move left and right, read and write. How are we going to utilize that to accept a to the n, b to the n? It's not quite the same logic that we had with NPDAs. Anyone have any insightful ideas about getting started? I think getting started, seeing a path to this is the hardest part of this. Once you have an idea, you can get it through to completion, but it's quite possible that you are stuck at that point. Any moments of brilliance? With an NPDA, with the stack, we ended up doing the equivalent of counting the A's and then mapping the B's to A's that we had seen in sequence. With a Turing machine, we don't have that stack, so we can't read a bunch of A's all at the same time and store them somewhere. we need to somehow match a single A to a single B, and then find a way to repeat that process. So when we look at the first A, what could we do to match it to either the first B or the last B? Something like that.
What if, now this may be like really wrong, what if for every A we turned it into a B and we kept moving right until we hit a B, and then we turned that into an A,
Kind of turned the problem into B to the N, A to the N. It's kind of, it's an equivalent problem that we then have to solve. How do we know they're an equivalent number? Thoughts?
Would be just, if you read an A, you go to a different state, you go all the way until you see a B. You go to a different state, go back until you see the second A, go back.
How would you know it's the second A?
By changing it to be a different symbol.
Yes.
That's
Smart.
X and Y.
Yeah. So we're going to use a tape alphabet that's not just A's and B's. We're going to use some symbol that represents an A that we've seen before and a symbol that represents a B that we've seen before. So start on the leftmost A, change it to an A that we've seen before, go to a different state. That will go until it sees a B. When it sees a B, it's going to change that B into a B that we've seen before, go to another state. We're going to move back left until we see an A that we've seen before, move right, that should be an A. Go back to the very first state and repeat that process of going back and forth, pairing A's, turning them into A's that we've seen before, finding a B, turning that into a B that we've seen before, until we go back to read an A and we find a B that we've seen before. When that happens, we know we've gone through all the A's. We then just have to verify there aren't more B's at the end of the B's that we've seen before. So with that idea, try to get those transitions down. That's a lot of transitions in a lot of states. This is a reasonably complicated Turing machine. See if we can write that out. We doing? Anyone think they have an answer? Couple people? Want some more time to work? Couple people? Let's take a little bit more time to go over a solution. To get a sense of the class, who feels like they're stuck? Few people? Good to know. I think we're about ready to see a solution. Let's go over how to do this. All right. We're going to start with each of the groups that I break down here at the bottom. So the transitions that fall into these categories, this is how I would construct a Turing machine like this. Is kind of a sequence of assembly-like instructions that adhere to each of the following methods. Because we can break down this process into those 3 steps. It's like we're going to iterate a loop of 1 and 2. So we need to define step 1 and step 2. The end of step 2 should take us back to the initial part of 1 so that we can repeat that. It'll complete a cycle in a state machine version of this. And then we want to, once we're done with that, once we reach a termination condition in that, we want to verify that there's nothing else at the end of the string and halt and accept. So here's group 1. We're going to start at an initial state Q0. And when we see an A there, which is what we expect to be the very first character that we're looking at, if A to the N, B to the N is on the tape, we want to convert that A into an X. And we want to change states because instead of looking for an A, we are now looking for a B. So we are going to move right, and Q1's entire purpose is to skip over a bunch of A's until we see a B or a Y. We want to skip over all the Y's as well, because the first time we're doing this, we just expect to see a B. But it's possible that until we go and see that first B, we're going to go over some B's that we have seen before as we do this. So we're also going to skip over the B's that we have seen before. The first time we do this, we've seen 0 of those, but in the future, we'll have seen some of them. So we're going to skip over A's, skip over Y's, and once we see our first B, then we're going to transition into a new state, Q2, with the purpose of now going back left and getting back to that first A. So this is the job of converting an A into an X, moving right until we see a B, and converting it into a Y. That's exactly what this sequence of instructions does. It's very low level, but it accomplishes that. Group 2's transitions, we said that was going to be returning to the leftmost A. So we need to skip over all of the B's we've seen before, which are our Y's, as we move back left. Then we need to skip over all of the A's we haven't yet seen until we reach an X. When we reach an X, that is the A that we've seen before, the first A that we've seen before, then we're going to do nothing, go right. What is right of the rightmost X? It's going to be the leftmost A. And that's going to put us back in that initial state Q0, where we're ready to convert that A into an X and move back right. So it gets us back to the initial position that we were in. Questions on group 1 and group 2 so far? How that creates a loop? Rush. Yeah. So that's group 1 and group 2. Group 3, so we're going to loop the converting an A into an X and a B into a Y. This will always work to convert an equal number of A's into B's. But eventually, when we return to the leftmost A, we're going to go right from an X. And instead of seeing an A from Q0, we're going to see a Y, the leftmost B that we've seen. If that happens in state Q0, that means we've parsed all of the A's. What happens if there were more A's than B's? Is that something we need to worry about? If we have AAB, we read the first A, we go over, we convert that into an X, we see the B, we convert it into a Y, we go back, see an A, but then we go past the Y, and we're going to see a blank. We're going to be in state Q1 as we're moving right, and we're going to see a blank. Is there any transition defined for Q1 on a blank? There is not, so we immediately reject. So it's actually embedded in this already. We don't need to worry about being more A's than B's. If we ever see a character that we don't anticipate, it's not an A or a B, there's no transition defined for that, so we don't care about that. But what happens if there are more B's than A's? We have something like ABB. That is not something that we handle here. It's going to look like we saw some A's, we matched them to some B's. If we just try to halt at this point and accept, that would be wrong. We would be accepting strings like ABB or AABBB, any string with more B's than A's. So we need to go to the end of the string and make sure that the last character before we hit a blank is a Y, saying that it's a B that we've seen before. Does that make sense to people? I don't see nods, so I'm going to assume that means no. We'll walk through an example. Let's walk through just what we have here in group 1 and group 2 and see what happens by the time we know that we need group 3 in order to ensure this. So we're in state Q0, reading this A. It tells us to convert that into an X and move right. So this A becomes an X, and we move right. As we do that, we move from Q0 to Q1. From Q1, when we see an A, we're going to just move right and make no change. Read an A, write an A. So we're in Q1. We move here. Q1 on a B says we're going to convert that into a Y and move left. Also moving to state Q2. So we're going to move left into Q2 and replace this B with a Y. Now we've paired off this X and this Y. We have an A that we've seen before paired with a B that we've seen before. Q2 is going to move when it sees an A, going to move left. So Q2 on an X, that tells us to move back to Q0 and move right. So we're going to, again, make no change, move right, back to Q0, and we're back to where we began. We've now made one loop of the process of pairing an A with a B. So looping around in state Q0, we're going to convert an A into an X. We know that when we hit that Q0, we're on the first A that hasn't been seen before. That's what we know starting this group of transitions. So we convert the A into an X, we move right and move into Q1. This is why we needed that move past the Y's in Q1 before, because this represents the B's that we've seen before. We want to go over those and pair the A that we just turned into an A that we've seen before with a B that we haven't seen before as we turn that into a B that we have seen before. So we'll move right, stay in Q1. And now we're pointing at the B, which tells us to convert that into a Y and move left. So we will convert to a Y, move left into Q2. And that tells us to move left until we see an X. So we will move left past this Y into there. Q2 pointing at an X, that tells us to move back to Q0. And we're back in Q0, pointed at the leftmost A, or the rightmost, the leftmost remaining A. In this case, there aren't any. So you would think that we could just move and accept, because we've now matched all of the A's to associated B's. But the issue is there could still be more B's at the tail end of this that we have not parsed. And we never got to that point to be able to notice that there were more B's. So that's what we need to do in this validation and termination step, is make sure that the A's that we paired with B's, there aren't more B's at the end of that. We know there aren't any more A's, otherwise we'd be looking at an A right now in Q0. So from Q0, we're going to move to Q3 and move right across all of the Y's. So we'll move past this y all the way to this b when we're in a new state Q3. And what we say is we're okay moving past y's, but what we expect to see at the end of all of the y's is a blank. We don't expect to see any other character. If we see any other character, the string is invalid and we should immediately halt and reject. So since we see this b and not this blank, we halt and reject. Even though we matched all of the a's to b's, there was still an aspect of the string that did not match the form that we are expecting. And because of that, we halt and reject. If we did get past all of the y's and there was no b at the end, the last character that we saw was a blank here, then we would know for sure that we saw the same number of a's as there were b's. There weren't any more a's, there weren't any more b's. So the string was in the form a to the n, b to the n. Questions? Confusions, clarifications? White flags? All right, so this is a pretty typical Turing machine type of program where we need to now really start thinking at a low level. It's very similar to trying to program an assembly. All right. Next thing we might care to do is go over AABB and write a sequence of instantaneous descriptions as it parses the input. Recall that instantaneous descriptions, you're going to write the string. Before the place in the string that the read-write head is pointed, you're going to write the state. And that's all the instantaneous description is. So when we start AABB, the read-write head is pointing at the A. I'll probably only go through a couple of these and then just reveal the full answer because this can be a long, drawn-out process that there's not a ton of value to past the first couple, making sure that you understand how it works. Well, I guess I'll start you off with the first one. So since we're pointed at the first character, we write the state before the character that the read-write head points at. Since the read-write head is pointing at the A at the very beginning of a run of this Turing machine, and we start at state Q0, we want to write the state before that first character. Then write the rest of the string, and we're good. What does the first transition do? It converts an A into an X and moves to state Q1. So the next one should be X Q1 ABB. We're not done yet. Gotta continue. Write a few more of these. Here's the full sequence, so you can check your work for what you've been doing so far. Any questions from these? Anyone get something different that they'd like me to explain? Right. Are we okay with these? Show a thumbs, how do we feel about instantaneous descriptions? For anyone without thumbs up, how can I help with that? I guess. What are any confusions? What are things that, where is maybe the better question, what can I go over that would help? Do we need to see, do we want to see an example? Do we want to see this derived, drawn out in more detail? Thoughts on that? To office hours it is, I guess. That's the case. Definitely do come talk to me in office hours, and I'm happy to work with you individually to help. Yeah.
I do have one question.
Yeah.
If we did Q3 goes to Q4 and then left instead of right.
Yeah.
And it ended on the Y at the end, reading Y.
Yeah.
Would that be okay? Like
that would be perfectly fine.
Okay.
In fact, I actually prefer it. I snipped this from the book. And for some reason, they like to move right at the end, creating that blank right before. Like we're looking at the second blank when we halt. It doesn't actually matter where we halt, but to me, that's kind of a. So I kind of prefer the left transition, but again, it's perfectly fine and correct. It just looks worse to me. You can do whatever your preference is. The last couple of minutes, I can talk briefly about Turing machines as language acceptors. So one thing that we may want to do is to be able to attempt to use a Turing machine to recognize a language that we proved was not context-free. I answer my own questions very frequently in here. We proved that this language was not context-free using the context-free pumping lemma. But how could we extend the prior program to now, instead of pairing A's and B's, to match A's to B's and C's at the same time? You don't necessarily have to write the program for this, but can we see how we could do that? Step one now would be turning an A into an X, a B into a Y, and a C into a Z. Then you would move back until you see your first X, move right, see an A, map that to a B, map that to a C, move back, continue that process. Any issues that you see with that as sort of why we wouldn't be able to do that with a Turing machine?
Yeah, two of the variables had different. So if A was, there's three A's and four B's and five C's.
3 A's, 4 B's, 5 C's. Let's read that and take a look at it. So we would convert this A into an X, this into a Y, this into a Z. We'd loop back around, we'd convert this into an X, this into a Y, this into a Z. We'd loop back around. This A goes to an X. This B goes to a Y. This C goes to a Z. We'd go back, we'd move forward, we see this Y. And so the two transitions that we'd allow in the verify and accept portion of this would be we expect to see nothing but Y's and Z's as we move to our first blank. If we see any character as we move to this blank that is something other than a Y and a Z, we will immediately halt and reject. And if we do that, then when we see this B and or this C, I should have done that C and not this C, that C still exists. So here is the first position that we would fail at. But we also would have failed here and here if we needed to. So I would argue that this is a great example of showing why this would still work. Any others? Any other string examples you think would cause this Turing machine idea to not work? It does work. And the conclusion that I will leave you to as we leave is that it turns out that Turing machines are more powerful than context-free grammars. They're more powerful than any kind of pushdown automaton, non-deterministic or deterministic. It can recognize all of those languages, and it can recognize more languages that context-free could not. So we will come back tomorrow and explore this in more detail. I guess we won't do that tomorrow. We're going to review for an exam tomorrow. I will leave you with this for almost a week, and then on Monday, we'll come back and talk more about it. Come prepared with questions tomorrow, and send me an email or come find me in office if you would like me to prepare some questions or some practice problems in advance of tomorrow on a particular topic that you feel like you could use some extra practice with.